All right. So we ended last time talking about this example that showed that when there's a massive pulley involved in a system, um, that the tension on either end of the pulley is different. And that's because if it weren't different, then the work done, then the work, how do I want to phrase this? If it weren't different, then the work done on each of the blocks would account for all of the energy change. And so the rotational kinetic energy of the pulley couldn't be anything besides zero. But if it's rotating, then it has to be something that's not zero. And so it just had to be the case that the tensions were different. So we're going to kind of in a roundabout way talk about why that's the case. And to do so, we need to introduce this concept of torque. Now, you guys have probably all heard this word before, but I want you to kind of set aside what your impressions of it are because it has very specific definitions and so on. So let's start with a question. If the net force on a system is equal to zero, is it possible for an object to rotate with changing speeds? i.e., is it possible for it to have angular acceleration? And just a little bit of thinking about it should indicate to you that yes, it's possible. We can just draw a picture. Let's say that we have a wheel, and you apply one force of some magnitude on the bottom of the wheel to the right, and then the same force of the same magnitude to the left on the top of the wheel. Well, in that case, the net force is zero, but we expect that applying these forces would cause the wheel to speed up. And that's true, that would happen. So this would be an example of the case that I just laid out. Now, in order to talk about angular acceleration, separate from translational acceleration, sorry, may as well write this down. Remember, angular acceleration is given by the Greek letter alpha. We need a second law for angular motion. And we also need a force equivalent. For angular motion. So just like how if we want to talk about acceleration of an object, translational acceleration, we need Newton's second law and we need force. If we want to talk about angular acceleration, we need some sort of angular second law and we need some sort of angular force. And so this force equivalent, that's what torque is. So torque has a rotational second law. Also that it has rotational work, impulse, all of the things that you can create once you have force, translational force, you can create with torque in a rotational sense. So we're going to try to understand how this thing that we're going to name torque works. So when an object's rotation accelerates, i.e. when alpha is not zero, parts of the object are linearly accelerating. That's an important thing to recognize. Just because it's rotation doesn't mean each part of the object is rotating. Each part of the object might be actually moving translationally. And so the fact that this is the case implies that regular force should play a role in torque. Like they're not completely separate things. They should be related. Just like how mass plays a role in moment of inertia, even though they are separate quantities, mass plays a role in moment of inertia. Similarly, we would expect force to play a role in torque. So the question is how? how does force play a role in torque? So I'm just going to draw an object. Let's say that there's a pivot point here. And let's say that we apply a force, say this way. Right? So I'm going to draw a vector, and I got to do this right. Dang it. Okay. Let me change what the force is, so then it's a little bit less obvious. There we go. So I'm going to draw a vector from the pivot to where the vector is applied. So, and this vector has a name. It's called r moment. Now, often we'll just drop the subscript moment, but for now I'm leaving it there because it'll be helpful. Now, this force can be broken down into two parts. Oh, this is a force F. This force can be decomposed like we normally do. It can be decomposed into a part that's perpendicular to r moment and a part that's parallel to r moment. So I'm going to call this segment of the force F parallel and this segment of the force F perpendicular. So let me just give some definitions here, or give some explanations here. So r moment, sometimes r mom, this is the displacement vector from the pivot point, or from the axis of rotation, those two are almost interchangeable, to the location where the force is applied. That's just how our moment is defined. Now, we know we can take a look and use our intuition at what the force, like if the force was just equal to F perpendicular or to equal to F parallel, what would happen? Well, that would be like pulling on or pushing on this object, like in this direction, right? And so that wouldn't actually cause any motion, right? That would just be putting like pressure or applying a force to the pivot joint itself. One way to think of it would be like if you have a door, it'd be like pushing parallel to the direction of the door. It doesn't cause rotation of the door about its hinges. So all this does is it pushes towards or away from the pivot. However, thinking back to the door example, if you push instead perpendicular to the let me bring you with me. Can you see a door? Yep. Yep. Right. Ooh, for example, the pivot being over here, if I push this way, that causes the rotation. That would be F perpendicular. If I push this way or pull this way, it doesn't cause any rotation. So that should probably agree with your intuition, right? You push perpendicular to the hinge if you want to make the thing rotate. That's just what we do. So that is all to say, F perpendicular directly is the part of the force that causes rotation. So indeed, the force does affect the angular acceleration. Now we can also make some other intuition-based assumptions. If we had pushed closer to the door, if we pushed closer to the pivot, the rotation would be less. One way to think about this is there's a reason why we put the door handle on the other side of the door from the hinge, right? Because it's easiest to push it far away from the pivot point. Similarly, if the perpendicular part of the force that we apply is small, the rotation is also less. So we know that there's a relationship between the amount of rotation that we get, this rotational force that we're going to call torque, and two quantities. One of those quantities is our moment. It's the size of our moment. How far away is the force applied from the pivot point? Because the larger that distance, the easier it is, the more effective this torque is. And similarly, the more force you apply perpendicular to this moment vector, the more effective your torque is. So the resulting consequences of these relationships is that the amount of angular acceleration is a combination. Mathematically, it's a combination of r moment and f perp. F parallel doesn't play a role in that angular acceleration. So the question now is, how do we actually combine them mathematically? Well, let's just draw a simplified picture. Let's say that this vector is r moment. And I'm going to even drop the subscript mom now. I'm just going to call it r. If this vector is f, then, and maybe that angle is theta, then this vector would be f perp. And so what we could say is we could say that f perp, the magnitude of f perp, is just equal to the magnitude of f times the sine of the angle between the force and the vector r. So that implies, or potentially it implies, that the torque is equal to the magnitude of f perp times the magnitude of the vector r. I'm going to put a question mark over here. Well, that will tell us how big the torque is, how much torque there is. But remember that just like regular translational motion, rotational motion also has associated directions. In particular, the right-hand rule tells us what direction a vector points in, given a rotation corresponding to our right hand. So the consequence is that we can actually write torque as a vector, because if the torque has an associated direction, that will tell us what direction the rotation will be in. So what we actually find is we find that the torque as a vector, and we abbreviate that with tau. This is the Greek letter tau. It's like a curly T. Is equal to the cross product of r cross f. Now, I did promise that cross products would be useful, and this is where we first see them. And you guys will remember from way back in the day, the magnitude of the cross product is the product of the magnitudes. It's the component of the force that's perpendicular to the vector r. Notice how there's a right angle here between f perp and the vector r, and the vector r is the vector that points from the pivot to the place where the force is applied. So the magnitude of the torque, you'll remember, is the magnitude of a cross product is the product of the magnitudes times the angle between them. And this is just the magnitude of f perp. So you can see that the cross product gives us precisely what we want. It gives us f perp times r in magnitude, and then the direction is determined by the right-hand rule. So these are the standard definitions of torque, and you can see that it involves both the location of the object, the location of where the force is applied, and how much force is applied and in what direction. And this is not so surprising. Everything that we've done with regards to things like moment of inertia and so on, when talking about rotation, it's very similar to the translational motion stuff. The one difference is that often the location of where something is matters. So when we talked about rotational inertia, moment of inertia, not only did the total mass matter, it also mattered where that mass was, how it was distributed. Here, it's not just the force that matters, it also matters where that force is applied and how the force aligns or doesn't align with the vector from the pivot point to the location where the force is applied. So both things matter now. Now, let's just take a step back and do some preliminary stuff. The units of torque are kind of strange. The units are given by Newton meters. And notice that these are the same as joules. Like a Newton meter is a joule. But I want you guys to never, ever, ever call the units of torque joules, because it just leads to confusion. Like, you don't want to say that it has 5 joules of torque. Typically, the language that you'll use is 5 Newton meters. And in fact, if you've ever been to Europe or looked into like European spec vehicles, when they talk about the torque of an engine, they talk about it in terms of Newton meters. Right. So okay, so that's what torque is, but we still haven't figured out how to discuss how torque, which we know somehow is like the angular equivalent of force, how does torque relate to angular acceleration? So for that, we need a rotational second law. Which is what we're going to cover now. So first of all, let's think about the direction of rotation. So in this example up here, the direction of the rotation that we would expect just by using our like our intuition, we would expect it to go counterclockwise, right? Because you're pushing on it one way, so you'd expect it to rotate that way. So we could figure out what is the direction of the associated torque. Well, torque is the moment vector r crossed with the force F. So we can figure out the direction of a cross product, r cross F, by using the right-hand rule. So I'm going to stick my left hand, but it's right hand for you. Stick my right hand in the direction of r moment, curl my fingers in the direction of F, and that tells me what direction the torque is in. So for this particular force and this particular moment vector, the torque is out of the board, or out of the screen rather. Now, what does that mean? What does that mean? That would mean that's going to so we would expect that it would cause rotation counterclockwise. But what direction? What is the associated direction of counterclockwise motion? Well, counterclockwise motion is curling my hands counterclockwise. That would also be out of the screen. And so the torque seems to be the direction of the torque seems to be in the same direction as the type of motion that is caused by this force. So just to summarize, the direction of motion which is counterclockwise, agrees. Come on, what is happening? Oh boy. Okay, 1 moment. Oh, it just crashed. Okay. One moment. There we go. Hopefully everything's back to normal. Right. So the direction of motion, which is counterclockwise, agrees with the cross product of with the cross product r cross F. Right, they match up just from doing some right-hand rule stuff. So that would lead us to conclude that the second law equivalent is the following equation, that the torque is equal to some constant times the angular acceleration, just like how force is equal to a constant, in this case mass, times translational acceleration. So the question now is, what is that constant? Well, in the linear case, in the translational case, it's mass. So thinking back to our analogies, or to our correspondence that we had before, mass, the rotational equivalent of mass is moment of inertia. Which is I. And so what we postulate then is that torque should be equal to I times alpha. So it turns out this is true, but let's do a sanity check just to verify. Just to check that this works out. So let's take a point mass tied to a string with the other end fixed. So in that case, well, let's just draw a picture. There's our point mass M tied to a string. That's our pivot point. So let's call this distance here, let's call it R. And then we'll apply some force to it, F, in that direction. So the force diagram for this particular setup would be, and I'm going to use a strange set of axes. I'm going to use plus y being down and plus x being to the left. So our force diagram looks something like this. We have a tension force downwards. We have a force that's pointing up and to the left. And then, oops, it's a curvy line. And then we would have this angle here, maybe we call that theta. This is F. So let's break down our components. So F sub x, the force in the x direction for this force F, well, that's the force in the left direction. And so that would be F times the sine of the angle theta. F sub y would be, well, sorry, this is F sub x net, F sub y net. That would be the, well, there's a upward part from the force F, and then there's a downward part from the tension T. Now, downward is positive, so we have T minus F sub cosine of theta. Now, now we know that the vector R points from the pivot to our point mass. And so the the y component is the component of the force that goes in the same direction as the pivot, right? So the F sub y net is equal to the mass times the acceleration. Sorry. Oh, this is terrible notation. I'm sorry. So disregard this idea of F or F perpendicular and F parallel as it relates to the moment arm, because we're not considering moment arms here. Remember back when we talked about moment of inertia? Sorry, not moment of inertia, centripetal force, there was parallel acceleration and perpendicular acceleration, and that was parallel to the direction of motion. So this direction is parallel. This direction down is perpendicular. And that's just because we're talking about parallel or perpendicular with respect to the direction of motion. In that case, the positive y direction is the perpendicular acceleration. That would be the centripetal acceleration, right? And then the net, the fx net would be the mass times the acceleration in the parallel direction. So I'll just draw some arrows for your notes. Parallel perp to direction of motion. This is not parallel and perp for the moment arm. We just use that. We abuse that notation, and for that I apologize. So let's take a look at just the tangential acceleration. The tangential or parallel acceleration is related to the angular acceleration. So imagine that you applied a big force to the left on this object, right? Well, it would both accelerate in the tangential direction, i.e. to the left, but also its angular acceleration would be large. They're related to each other because the tangential acceleration is how the speed is changing as it goes along the circle or goes around the circle. And so that relationship is the same relationship that we see for all of these rotational translational relationships. In particular, the tangential acceleration, the parallel acceleration, is just r times the angular acceleration. Now, the reason why we're doing this, by the way, is to check to make sure that this formula makes sense. So far, we haven't actually done anything. All of this business is just old stuff. Like, that's all stuff that we've talked about before. Now we're going to try to relate it to the angular quantities to see if we can actually get the same result by using this torque tau equals I alpha formula. So let's step back and now let's reframe this in terms of rotational motion. So the rotational inertia for a point mass, well, we know how to calculate that. Just for a single point mass, it's just the mass times its distance from the pivot squared. So in this case, it's just mr squared. So f sine theta, which is equal to m a parallel, well, we can substitute in, we can use our moment of inertia to solve for m, and we can use this formula to solve for a parallel. So this is equal to I over r squared times r alpha, right? Just all I'm doing is substituting in what m is in terms of its moment of inertia, substituting in what a parallel is in terms of its angular acceleration. And so we can do some simplifying, and we get this is I alpha over r. I promise we're getting somewhere with this. And so rearranging, we get that r times f times sine theta is equal to I alpha. But this thing here, this is r times f times sine theta. That is just the magnitude of r cross f, where r is the vector that points from the pivot to the location where the force was applied. And so this is equal to the magnitude of the torque. And so it checks out. The magnitude of the torque is equal to I times the magnitude of the angular acceleration. So this example was all just to make sure that this formula makes sense. We derived it just using regular Newton's laws and some relationships about how the angular acceleration relates to tangential acceleration and how the moment of inertia relates to mass. And just by using those facts and using regular Newton's second law, we get that the torque is indeed equal to the moment of inertia times the angular acceleration. Now, the reason why these are all just magnitudes is because this is just a 2D problem. So just like it's just 2D rotation. So just like how you could just work with positive and negative numbers in one-dimensional motion, for rotation in a 2D plane, you can just work with positive and negative numbers. So with that in mind, now that we have this rotational second law, the only difference now, if you want to solve a rotational problem rather than a translational problem, the only difference between solving a rotational problem and solving a translational problem is let me actually write this down. Between translational and rotational problems. So first difference is that you now have to do cross products. So if you want to find the force equivalent or the torque, you have to do a cross product. And B, you have to know how to find the moment of inertia. So you need to, so it's certainly more involved, but not a whole lot. Like once you know how to find the torque, which is just a cross product, once you know how to find the moment of inertia, which there are a whole bunch of different methods for doing, parallel axis theorem or integrating and so on, then it's just a matter of you find the net torque, you find the moment of inertia, you solve for the angular acceleration, you plug that into your kinematic equations and so on. And it's just, from there, it's just exactly the same. So let's do another example. Let's test this on another example where we actually know the answer. So the example that I think we talked about this on Monday. It was for a spool that's unraveling because like a block is hanging from it. So this radius is r, the spool has mass m, and the block is falling and it has mass little m. So the question that we want to answer here is, after m, the little block, falls a height h, how fast is the block moving? That's a question that we can now answer. In the past, the equivalent type of question, if we were not doing rotation, would be, if a block is falling, after a block has fallen h units, it's not tied to anything anymore, it's just falling. How fast will it be falling? Well, there are two ways that we could do it. The way that we solved this problem before was we used energy conservation. So you could use energy conservation to figure out how fast a block will have fallen. Sorry, how fast a block will be falling by the time it's fallen h units of distance, just by setting change in potential energy plus change in kinetic energy equal to 0. Alternatively, you could use kinematic equations. You know the force downwards on the block, so you know the acceleration, and then you can solve for the speed after a given amount of time and so on. So we're going to do the second method here, but using rotational methods. So we already know the answer using energy conservation methods. Now we're going to use rotational kinematic methods because we know how to handle rotational motion now. So to do that, we need to draw extended force diagrams. So these are basically regular force diagrams, except now it matters where you put the force. So there are two objects here. There's the spool, and there's the block. So the spool certainly has a force downwards. It's a tension force downwards on the right. Now, it's connected to this central axis at the center, and so there'd be a normal force holding it up. Now, I haven't explained why yet, but it is true that the gravitational force also applies at the center, and obviously it goes downwards. Now, for the block of mass little m, the force diagram looks basically the same as you've been drawing it. I'm not going to put a thing there. So again, gravity acts from the center downwards. I'm going to put a capital M there and a lowercase m here. And then the tension force acts from up here, upwards. Now these are the same tension force. There is no pulley in the way, so they just are the same. So we need to figure out what the net force, what the net torque, and what the net forces are. So then we can use our Newton's second law equivalence. So the net torque, and by the way, because this is a two-dimensional problem, it is sufficient to just use non-vectors for our setup. So in this case, I'm going to define counterclockwise as positive torque, and I'm going to define up as positive y. This will make sense in a moment. So the sum of the sum of all of the torques has to be equal to I alpha. And the sum of all of the forces in the y direction has to be equal to ma. Right? So let's figure out what the sum of the torques are. Now, first and foremost, these are magnitudes, is what it boils down to. So, or these are not magnitudes, but they're they're scalars with positive and negative signs. So let's look at the torques that would be generated by N and F and the gravitational force. Well, we know that the magnitude of a torque from a certain force depends both on the magnitude of the force and how far away it is from the pivot. But looking at this example, these forces originate at the pivot, i.e. that distance r is 0. So the torque from the force N is 0, as is the torque from the gravitational force. They're both 0. That's just because those forces originate at the pivot. However, the torque from the tension force, well, so we know that the torque from the tension force is going to be clockwise. Actually, let me choose this direction to be positive, just so there's not an extra minus sign floating around. So the torque, we know it's going to go in the clockwise direction because that's the direction it's pulling on. Hopefully you guys can kind of have intuition for why that's the case. The distance that this force is from the axis of rotation, that's just r. It's just the radius of the spool. Remember that the magnitude of torque is just equal to the distance times the magnitude of the force times the sine of the angle between them. So the distance is r, the magnitude of the force is t, and the angle between them is 90 degrees, right? There's a right angle here. So the sine of 90 degrees is 1, so it's just 1. So the torque for the tension force is just r times t. Now, so that implies that the sum of the torques, the net torque, is just RT. So RT is equal to I alpha. Okay, so far so good. Now what about for the force in the y direction? Well, that's just easy. We have plus T minus little mg equals ma. And that's it. It's just normal Newton's second law. So we have these two equations that we need to solve and learn about, or that we need to use to learn about the system. But it seems like we don't have enough yet. However, we're missing a few things. There are some constraints, or there is a constraint. The constraint is that the speed at which the block falls is related to the speed at which the spool turns. In particular, this is like rolling without slipping, and so we would expect to see a rolling without slipping type condition. In particular, we get that A is equal to R alpha. Further, we have a relationship between the moment of inertia and the mass of the object. In particular, for a spool, for a solid spool, this is 1/2 mr squared. So now we can solve. Now we have enough tools. So we have RT equals I alpha, and I'm going to substitute in what I and what alpha are. This is 1/2 mr squared times, well, alpha is A over R, which is just 1/2 mRA. And so what we find is that A is equal to 2t divided by m. Okay, we're not done yet. We also have this second equation that we haven't used yet, which is T minus mg equals ma, right? That's just Newton's second law in the vertical direction. Oh, I haven't fixed this yet. It's annoying. So I always have to double check and make sure that this is right. So I chose up to be the positive direction, but I really shouldn't have. And the reason I shouldn't have is because if torque is positive in the clockwise rotation, then we need the signs here to be correct, right? So when A is positive, this would indicate that alpha is positive. But A is positive when it accelerates upwards, not downwards. So all I'm going to do is I'm just going to change the convention that we have here. Actually, no, I'm not going to change that. All that will do is it will just make this a minus MA. because we're assuming, oh, no, that's fine. This, I still haven't corrected this in my notes. I always need to double check this and make sure that this works. I mean, it does work, but yeah, let's just change the signs everywhere. So that way then everything agrees with each other and then we don't have to worry about it. All right, so plus y will be downwards. So that means that our formula becomes mg minus t. And then this is equal to ma. And then when a is positive, alpha is positive, so that checks out. And so now we have, okay, so now we can just go back and we can continue. So we have mg minus t. All I've done is I'm using a different set of coordinates to be consistent. This is equal to ma, by the way. All right, so we have mg minus t equals ma. And so we can rewrite that and we get that t is equal to m times a minus g. Sorry, g minus a. Yeah. Right? Everything checks out. Move that over. Yeah, okay, g minus a. And so then we can use that, well, we know what a is. Here, we know it, and so we have two equations and two variables. We have that a equals 2t over m and t equals m times g minus a. And so we can combine those two results to get that a is equal to 2m times g minus a over m. All I did was I plugged in t back inside there, right? And so we can solve this equation. This just gives us that a is equal to 2mg divided by m plus 2 little m. So now, just looking at this equation for what the acceleration is, that's the downward acceleration of the block, we see that it's positive and constant, right? The fact that the acceleration is constant tells us that we can use our standard kinematic formulas that we like to use. So that is, we can use the formula vf squared minus vi squared equals 2ah. That's totally valid. And so we would get that this gives us the f squared minus 0, starts off at rest, is equal to 2 times 2mg over m plus 2m times h, or equivalently, that vf, this is the final speed of the block, is the square root of 4mgh divided by capital M plus 2m. And this result that we just obtained, this is the same as what we had before by using energy considerations. So all we've done is we've used torque and the rotational second law in combination with the standard second law to solve a problem that we also solved with energy considerations. And so it works. Now, this sort of problem solving can be tricky. You have to use constraints like how various accelerations relate to each other. You have to know things about the moment of inertia. You have to write out what the net torque is. Remember the formula tau equals I alpha, the rotational Newton's second law, is really a statement about the net torque is equal to the moment of inertia times the angular acceleration of the system. But in principle, it's more or less the same, just with more stuff added. It's like there's conceptually there's not a whole lot new. The tricky bits are just knowing how to compute the torque, which we do by using a cross product, and what the moment of inertia is. And then sometimes you'll have these constraints, but these constraints are basically the same as like a constraint on static friction or kinetic friction or whatever. And then all I did was I just used the standard kinematics to solve for the speed. All right, so we're going to take a slight detour to rotate to the land of rotational work and power. I promised that these are things. So I'm going to show you how they work. And they're really not, it's really nothing conceptually new. So we're going to just directly translate from the linear case. So in the linear case for work, we have the work done as the object that goes from A to B is just equal to an integral from A to B of the force dotted into the path. And that was equal to the change in kinetic energy, which was just 1/2 mvb squared minus 1/2 mva squared, right? Nothing new there, work energy theorem. The rotational version is just the same, just by substituting in the new things. So the work done as it rotates from angular position A to angular position B, think about like a gear rotating from here to here. That's what we mean by from A to B. They are the rotational configurations. This is an integral from A to B, again, rotational configurations, of the torque. We just replace force with torque, and we replace distance, dl, with a change in angle, d theta. So this is just a small change in angle, basically, just like how dl is a small change in position. And this is equal to the change in rotational kinetic energy. I'm going to put rotational there, and I'm going to put translational here, which we know the formula for. It's 1/2 I omega b squared minus 1/2 I omega a squared. So all we did is we just substituted in the variables that are appropriate, and everything works out the same. So just to be clear though, this vector, that vector is the vector that you would get, or it points in the direction of the direction that your thumb points in when you use the right-hand rule, which indicates a small amount of rotation in a direction. So if we were talking about a small rotation in the clockwise direction, that d theta would have magnitude d theta and would point into the board, or into the screen rather. That's the direction it would be from the right-hand rule. Now, I promise this would be a short detour, but we just have one more thing to talk about. That's rotational power. So just like for translational motion, we have that power, regardless of whether it's translational or rotational or whatever, it is the time rate of change of the work. And so if we're talking about rotational motion, it's just the derivative of this integral, which pulls it out of the integral. And so this is just torque dotted into omega, just like how the power for translational motion was force dotted into velocity. Just the same thing. P equals F dot V. It's completely analogous. So that was just the short detour I wanted to take. So this is how you can compute the power output of like an engine, because that engine is not something that's being pushed in a direction. It's like the engine is rotating. So you would have to find the torque output of that engine and dot that torque into the angular velocity that the engine is currently rotating at. And that will tell you how much horsepower the engine puts out. So if you want to go do a quick test, and by the way, the assumption is that the torque typically points in the same direction as the angular velocity. So for the most part, these are just in the same direction. So it's just, the dot product is just the product of their magnitudes. So if you want to go do some checks on your understanding of physics, go look up the torque output, maximum torque output of your engine, of the engine in your car. Go look up the maximum cyclic rate of your engine, or of the pistons. How many times or how many RPMs does it get? Multiply those numbers together, convert the units appropriately into, it'll initially be in watts if you take torque in Newton meters and you take angular velocity in radians per second. Multiply those numbers together, you'll get watts, convert it to horsepower, and that should probably agree, at least close, to the maximum horsepower of your engine. There's something to be said, though, that the maximum torque doesn't always occur at the same time as the maximum angular velocity or the maximum RPMs of your engine. So the maximum horsepower will probably be actually less than what you got, but that's a technical aside that isn't super relevant here. Right, so I guess it's 11:49, so I'll end it here. We're going to start next time talking about static equilibrium, which is kind of what you need for the homework. You can do some of the homework with what we've covered today, but we'll need more. We'll see how far we get on Monday with that, and we'll so I guess we'll proceed from there. All right, so I'm going to end the recording here.